And you've seen this clean room classification systems, right? There are three major ones. So the so-called federal standard system developed by the US. It's following the imperial system, of course, the scale footage instead of scale meter. And then there's that ISO standard. It's kind of international standard according to the metrics. Okay. So the cleanest area in the federal standard is class 1. It goes class 1 through 100,000, right? 1, 10, 100, 1,000, 10,000, 100,000. So those are actually number of particles that are allowed within a cubic feet space. Okay. And then international standard, of course, is ISO 1 through ISO 9. So cleanest is, of course, ISO 1, but the equivalent clean room designations, class 1 is equivalent to maybe ISO 3. So that's the cleanest area you can see. Maybe class 100. So in the drug manufacturing, you don't use class 1 or ISO 3. Actually, you start out from class 100, which is ISO 5. That's the cleanest area in your manufacturing process. So that is probably inside of the filling machine. That's the cleanest area, class 100 or ISO 5. That may be same as grade A area in the European system. Okay, and it goes down, and maybe ISO 7 is equivalent to class 10,000. Okay, ISO 8 and 9 and that order. Okay, and then again, so there's the European system that's used a lot these days. So like I said, three different classification systems: federal, ISO, and EU system. So EU system is much simpler. There are only 4 different grades, A through D, right? A being the cleanest area, D being the dirtiest. Okay, so in the at rest, in operation, they have these guidelines, how many particles you can have, right? Then how do you compare all three? If you compare all three systems, it's like this. Grade A, like I said, the cleanest, is equivalent to ISO 5 and maybe federal standard, maybe class 100. Those are cleanest area inside of a clean room, right? The filling machine, inside a filling machine, the cleanest area. You cannot go in there, even you are fully gowned up. Nobody's allowed to go in there. And then next clean area is grade B. That's outside of the filling machine, where people are standing, doing some work in the clean room. Of course, that's they're fully gowned up aseptically. That's ISO 7 and class 10,000. And then grade C is the next clean area, maybe ISO 8, class 100,000. Okay, and the dirtiest area would be ISO 9, class maybe million, and grade D. Okay, so that's the order. Okay, so you understand this chart is very important because these are relevant spaces that you use in your manufacturing. And of course, the clean room is maintained by the HEPA filter, of course, right? So it's a laminar flow of air through the HEPA filter coming down from the top of your ceiling and goes down. It's recirculated, and HEPA filter should be tested at least twice a year. Okay, how do you test it? Use a special gas. That's polyalpha olefin, PAO aerosol. So this picture shows you how you test it. Aerosol makes kind of a droplet that's large droplet, 0.7 micron size. So if that aerosol is coming through your HEPA filter, then there's a problem, because it should not be, and all these aerosol should be trapped because it's large enough to be trapped, right? So that's how you validate your HEPA filter. That should take place at least twice a year. Okay, so let's say inside of area, inside of the filling room where operator standing, let's say maybe grade C, I said. Okay, and that's the inside of filling machine. Okay, anyway, so yeah, that's what I'm talking about. So this is what I'm talking about. So maybe ISO 8 is where these people are standing, and this is filling machine. Of course, this is during the line clearance. That's why there's no gloves in the glove compartments. Okay, but if it is during the process of manufacturing, this should have the glove all filled in, and the filling should take place in there. So we're talking about inside of this filling machine. That is a cleanest area. That's probably grade A, ISO 5, class 100. Okay. So flow plan of your manufacturing process. The design is very important because the design is such a way that only the unit flow of manufacturing should take place. So that will prevent any mix-up, right? So unidirectional flow should be considered in your design of the manufacturing space. So if it's a formulation, the raw material coming into the space warehouse, and then maybe QC check, and then staging, and then formulation, and then after that maybe filling machine, filling taking place someplace, and then packaging and the finished goods in the warehouse. So see unit flow design processing. Okay, and this should be a clean room. Okay, and then the office area, maybe something like that. So if you go to Catalan, you will see that kind of design reflected based on this. And the barrier isolator technology is very important because the clean room itself is not enough. When you fill your sterile drugs, you have to create that, cleanest environment, great area. So you need to have barriers or isolators inside of a clean room. Okay, so that will give you a separated space where a very clean operation will take place. So isolator design is more dependable than barrier design. So what's the difference? So this is a barrier and this is isolator. So can you see the difference? The difference is the barrier doesn't have the HEPA filter unit by itself. Okay, it's just a kind of wall, segregated, I guess walls. So it just depends on the clean room air filtration system. But isolator by itself has a HEPA filter. Okay, so it's placed inside of clean room. So it provides more protection. Okay, so see those globes are placed in the compartments. So now, yeah, that should be the case. I don't know if this picture came from Catalan or not, but yeah. So these people do not wear masks and face masks and things because they have good protection in there. Okay. So barrier isolators are used often, and they are ideal for a very economic reason. They protect the product from human contamination, so used a lot. Okay. They provide complete isolation of the inside of the isolator. That's inside the class 100 ISO 5 grade A area. Okay, and outside maybe ISO 7 or 8. Okay, depends how they designate it. And there are RAP system, which stands for Restricted Access Barrier System. Restricted Access Barrier System. Okay, and RAP system provides sub-isolation protection, but are far better than the laminar flow hood. Okay, there's an active and passive RAPs. Okay, so the difference is, does it have its own HEPA filter unit? If it does, then it's an active RAP. If it doesn't, it's depending on the the HEPA of the clean room. It's a passive system. So that they are good protective unit. So RAPs and isolator systems use glove ports, like I said, and rapid transfer ports. So if you bring in some materials, you use the rapid transport. Okay, so disinfection is typically manual in the standard RAPs, but there is no operator human access to the isolators as their product contact parts are clean and sterilized in place. So CIP, SIP. So what it means is you're not allowed to go in there. So it is done automatically. Normally it's the gas sterilization method. So during the line clearance, you maybe clean up inside during the line clearance only, and if it's all cleaned up, you seal it up, and during that manufacturing, then you'll never clean up. It's automatically done. That's what it means. Okay, maybe vapor phase hydrogen peroxide. That's what you will use to sterilize it. And validation of barrier isolation, air supply specification. Is there enough air change happening at the right rate? Air velocity should be checked, particulate air specification, recirculation rate, temperature, humidity, aeration, all those things should be checked. And leak testing is important because there should be any gas leak. So pressure decay test will be taking place. If there's no leak, pressure should be maintained. And there's a trace of gas detection. So if gas is leaking or not, you can test that. and RTP, rapid transport port, and there should be good seal there. Seal integrity test to be done. Facility requirement, of course, classification of isolated room, temperature, humidity control, process utility, all those things should be all maintained well. Usual requirement, of course, sterilization, decontamination of methods, cleaning, contamination, environmental control, monitoring, microbial monitoring, process simulation. That should take place. Okay, operational qualification. All alerts and alarms should be tripped and verified. Integrity check should be verified, and they should be free of any leak. Sterilization cycle verification should include temperature, humidity control, as well as the concentration and distribution of saturation gas during the sterilization cycle. Makes sense. And sterilization cycle development, so you have to prove that, yeah, your sterilization method is really killing the contaminants. So you can use maybe biological indicator such as Bacillus, Stereophilus cells are in there, and you need to place that during the sterilization cycle and see if it's really killing. So the log reduction should be demonstrated. Okay, so here's a burden of validation. Okay, let's talk about water and air quality, of course. So water is used a lot because you need so much of the water as a solvent during the production. Okay, so your formulation, water is the main solvent, and when you clean, you will use water for your cleaning process. And when you do SIP, of course, steam is generated by the water, UFI water, and the cooling system is also using the water. So water is used in so many different parts of your manufacturing. Okay, so then what kind of water should you use? According to US Pharmacopoeia, the water should be good, so it can be injected into a human body without causing any problem. So it's water for injection is the water required for your manufacturing UFI. And the endotoxin, you cannot have a lot in there. So only 0.25 EU per mil is the required amount of endotoxin. So of course, less than that is fine. So then how do you purify your water? So feed water, maybe tap water, should be purified through maybe multimedia filter. Okay, maybe the beginning filtration will take place, and then softener. Okay, you can maybe get rid of iron using iron baths and things like that. And there's active carbon filter, so there's charcoal there, so remove organic material there. Okay, and then UV sterilization may take place, and then another filtration. 5 micron pre-filtration will take place, and after that, when you go, there's ion exchange to remove any charged ions, so that takes place, and then another ion exchange. If there's maybe cation exchange, there's an anion exchange, you remove both, and then another 2 micron final filtration take place, and then what's happening after that? Distillation. So yes, distillation after that, and after maybe ultrafiltration, and then so if it's just ultrafilters, it's stored used for something else. If it's distilled, and that's OFI quality, stored somewhere else. So that's the OFI quality. So many filtration, so many using charcoal and iron baths and different filters, and then this distillation. By combining all those, you can generate OFI quality water. That's how your UFI water is generated. So UFI is prepared by distillation, reverse osmosis, or ultrafiltration, and the European standard requires similar quality water, Japanese international standard as well. Potential impurity in feed water, seed water, it has a lot of bacteria, maybe endotoxins, particles, electrolytes, organic colliders, and all those things. They should be removed, even chlorines as well. So water purification method includes all those things. Distillation, of course, is the boiling of water. You collect the vapor and you cool it down to get the liquid water again. Okay, so let's stop.